بسم الله الرحمن الرحيم والصلاة والسلام على نبينا محمد وعلى آله وصحبه أجمعين. Thank you everyone for being here. I'm very glad and delighted to welcome today Professor Eric Feron, our distinguished visiting professor from KAUST. Today, Eric is going to provide us a presentation on building safe autonomy with unproven algorithms. So let me give a brief introduction about Professor Eric Feron. He's a full professor in King Abdullah University for Science and Technology. He's a computer scientist and aerospace engineer. He has been a professor of aerospace software engineering at Georgia Tech since 2005. He taught at MIT Department of Aeronautics from 1993 until his appointment at Georgia Tech. He obtained his bachelor's degree from Ecole Polytechnique, his master's degree from Ecole Nationale Supérieur, two very prestigious universities in France, and PhD from Stanford University. His particular research focus are in aerobatic control of unmanned aerial vehicles, multi-agent operations, including air traffic control systems and aerospace software system certification. I'm very glad to give you the token to make the presentation, Eric.
Thank you very much. Do you hear me on the microphone? Yes? Okay, very good. So first of all, thank you very much, Professor Anis, for welcoming me here. I must say our friends from the Cyber and Drone, Cybersecurity and Drone Federation, I should thank you very much for giving me the opportunity to attend my first meeting where I met with Professor Anis. And just looking at him and listening to what he was saying, I said, there's a lot of energy there. And so that is how that is the first meeting that, and I thank you very much for offering this opportunity for me to meet with Professor Anis. And then that led to a few things, including Professor Anis's participation to a robotics conference that was held about 2 weeks ago at KAUST. And then it is then that I realized that if I thought Professor Anis was about this big, in fact, he is this big. So, and I'm very honored that you invited me here. So, so let me give you a little bit of further background. So I've been interested in flying machines for quite a while, and I pretend to work on safety. And well, what is safety is keeping away from trouble. It's always something that is important. It is not far away from security. Because it's the same kind of statement that you want to satisfy, which is always stay away from trouble. Okay, that's what it means. And there is even deep mathematical consequences to this. You can, maybe you can think about it with your kids. Okay, keep away from the stove all the time is much easier to do than say, promise me you will do your homework tonight. And these are two statements that are actually very different. One of them is a safety statement. The other is a liveness statement. And liveness is so much harder than safety. So so I've been interested in safety in the context of a lot of things. I've been looking at problems of automotive with Ford. I've been looking at problems of drones. I've been also looking at problems in air transportation. And so my philosophy is sort of influenced by all these activities. Also, another thing is you see this word unproven algorithm. So part of my training is what people call operations research, where we try and use all sorts of algorithms to perform trajectory planning and things like that. these algorithms work very well in practice, but often we don't have too many guarantees about how they work in theory. And so it is, of course, close to my mind to be able and have a safe system with unproven algorithms. Thus the topic of my talk and the few things that we have been able to discover in this area. Today, there is a significant program in the US about what people call safe autonomy or safe artificial intelligence and things like that. And it's always the same things. How can we use fancy algorithms, but without endangering the system, knowing that in order for the system to be absolutely safe, we only know one thing, okay? Go a straight line and use PID controller to control the system. That's it. So before I go any further, I want to add and advertise a little bit my colleague Shinkyu Park. He just arrived at KAUST, and he's a brand new assistant professor, and he's going through all the trouble of being a young assistant professor, which is he's discovering a lot. So he just joined, and I'm very happy that to have somebody I can play with, like right next to my office. So here's the core message in when we talk about safety and with unproven algorithm. So the idea is when you have your robot do something, say from point A to point B, you plan for safety first, and you make progress if possible, progress towards your goal. This is not always possible. I will show you an example, but in many cases, it is possible, and it creates very interesting problems. So I will talk a little bit about the general context in robotics and the need for increasing safety. I will talk about what I call the Ariadne principle, and I will talk about also issues of how it looked like in the past, in the present, and in the future, and then I'm going to talk about what's coming next. So the robot world has changed quite a bit over the past 60 years. 60 years ago, this is what we had. So robotics is about 60 years old now. At least the first industrial robot that was actually used is 60 years old. And you may notice, so the source is the Henry Ford Museum, but they don't say which factory it was used at. Can you guess? General Motors. So, the interesting thing is that at that time, the robot was used to do things that no human should be doing. So in this particular case, it was taking a part that was like really hot, and it was putting it into a bath of cooling liquid to sort of strengthen the part. And these robots would be like really far away from humans. They would be, well, they would take care of a task which is very, very dangerous to humans, and they would, by design, not interact with humans. So there would be no problem of safety. By the way, at that time, it was hard to figure out which was the robot and which was the computer. Everything was integrated together. Okay, it was. If you look at the architecture, the information architecture, inside, it's hard to understand which part is the robot, and which part is the mechanical, and which part is the information system. So the things have changed quite a bit. So this is more or less what things look like now. I will ask you to pay attention to the motion of the human next to this manipulator robot. So I don't know if you saw all the details of the movie, but in this case, the robot is a much lighter, is much more agile, and is a lot closer to the human. And did you see what the human did? Yes, but you also move sideways at some point. You're like, whoa, the tray is coming a little too close to me. And so there is also a much more interaction or potential interaction between the human and the robot. And that creates, of course, new things and new problems that were not there in the environment, the manufacturing environment 60 years ago. Otherwise, the donuts, they look good. So I would add that also the robotics world has changed quite a bit in terms of like where the robots go. I would say that the human is a lot farther away from the robot as well. So it can be either a lot closer or a lot farther. And the robot can be a lot smarter. So this is a picture of a former student, Olivier Toupet, just a few, maybe hours after he learned that the robot, what's the name again? Perseverance had successfully hatched the little helicopter underneath. And that same little helicopter is supposed to start flying when? Today, exactly. Okay. So I couldn't resist putting this picture. Olivier is in charge of some of the helicopter operation, and at least the hatching area, the hatching operation was successful. And you can see that he was reasonably happy. Now, in this case, there is no safety problem, meaning if the helicopter doesn't fly, nobody's going to die. Okay, but on the other hand, it is still a very, 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 very expensive robot. Whether it is opportunity or now perseverance or ingenuity, the robot that is the little helicopter, they are really expensive. They are really expensive systems. Okay, for the little helicopter there, the price tag, as they talk about it, is $80 million. So it's about 100 human lives, according to the people who dare putting a price on a human life. And so that's about one, and it's also about one full Airbus A320. So it's expensive for a teeny bitty, itty bitty thing. So what does that mean? That means that the concept of safety, meaning staying away from trouble, also applies to these extremely expensive programs. And so I have a backup plan in case the helicopter doesn't take off today. I just couldn't resist showing it. My dream is to make like a Mars-like ambience on Earth by having a 747 fly a parabolic trajectory. I think we can get 30 seconds of flight time as if we were on Mars, and then we could take off and land and do everything on Earth before we spend $80 million going to Mars. So that's my backup plan in case in case there is a problem today. I hope there is no problem. In case there is a problem, I have a backup plan for next time. So, oh, thank you. So the problem of ensuring safety in a complex system is not a new problem. And for any safety critical system, there are very, very rigorous processes put in place so that starting from a concept and a set of requirements, you end up with a system that works. For that, we have, for example, very rigorous design processes. One that's fairly well known is the V design process that makes sure that everything that is being done is documented, traceable, and that for every design operation, there's a corresponding verification or validation operation where the verification and validation can be traced back to exactly what was done at the design phase. As you can imagine, things are arranged so that you maximize the probability of finding a problem early in the process and not late in the process, because the later you get into the process, the more you're going to have to pay for this. Okay, you, as part of these, in the case, for example, software design, you have lots of tools to do not only design but also verification, validation. Most of the manufacturers of what we call safety critical software, so drones and things like that, use verification tools for their software. The names of these tools include Polyspace from the MathWorks, or Astray from Absinthe. It doesn't matter the name; they all came from the same person in France named Patrick Couzeau, who is as genius as he has a bad temper. And we have these tools, and of course we can also think about redundant architectures. It's a very important part of the design for safety, that your system be able to be fail-safe, and you have significant regulations, written documents that explain to you everything that you should be doing. Usually, people who are sort of action-oriented considers that those regulations are the boring part, the part that's going to be very painful to pass, because you're going to have to convince all these people at a variety of organizations, including the organizations in charge of drones, that whatever you design will be flying without creating problems. Am I correct? So, as I said, all these processes and regulations and architectures are supported by technologies, and then they go from simple technologies such as tracing technologies to more mathematical things: risk analysis, fault tree analysis, static software analysis, FMEA, etc., etc. And so there is this balance of regulations and processes together with technologies that help us sort of come up with systems that work in the end. I teach an online course that was recorded at Georgia Tech, but is available on Udacity, that's named Cyber Physical Systems. And I try to cover a little bit of all this, even though it is impossible to be comprehensive. And next fall, I intend to start offering the course at KAUST. So we now have a software revolution. Over the past few years, we have suddenly seen this great enthusiasm for new sensory capabilities, revolutionary image processing techniques, and revolutionary hardware. We have convolutional neural network, other new and very efficient ways for a machine to have a better situational awareness of what goes around it. That's on the one hand. On the other hand, we also have new algorithms and models for behavior planning, including deep learning, random trees, random networks, integer programming, linear temporal logic. Okay, and let's not forget, of course, the human does also a lot of the planning. Okay, and in the rest of my talk, this is what I will be mostly interested in. The sensing and the idea that you have a very reliable sensing is a question that I don't feel qualified and comfortable addressing. There have been some work, for example, provable deep convolutional neural network, provable perception, and things like that. But we know that it is a very difficult problem. On the other hand, I think I can do something about these new algorithms that we are learning about, we are implementing. Some of them a while ago, but many of them now. There is this big interest into doing fancy planning, but if possible, safely. Okay, and so the main issue that arises is what if the algorithm takes me in an uncomfortable situation? Right? You know what happens, right, Professor? When you hire a genius, you're certainly very happy that the genius is going to do all sorts of good things for you. Okay, but you're always worried that the genius might go also like very wrong. That's the downside. And so you want to make sure that you have a genius that you can keep in the bottle when necessary. And so let me give you some examples of like really bad functioning algorithms for really bad accidents. So this is the case where the algorithm is a human. Okay, so it's just the human brain that does something. And it's the case of a genius that did something really stupid. There was a famous plane crash that happened as follows. So a Wichita State University football team had to play somewhere in the Rockies. They flew from Wichita, Kansas, I think it's Kansas, to Denver. They made a stopover in Denver. And then the pilot said, let's have a little fun. And they decided that they would fly the airplane inside a valley. And it was just to show how beautiful the valley was, especially when the airplane flies among mountains that are higher than the airplane. Okay. Little did they realize that the planning they were doing and the flying they were doing ended up in a dead end. So there is the airplane flying in the valley, and then the mountains going up. At some point they arrive, and the valley closes. The airplane could not go over the mountain anymore, and it could not make a U-turn because the valley was too narrow. In other terms, what they were doing is they were doing a kind of step-by-step planning, figuring out what they're going to do over the next 5 minutes, but without looking far enough, and the airplane crashed because they tried to make a U-turn, but they did not have enough room, and they crashed. So the airplane was basically dead even 10 minutes before they realized they were in trouble. Okay, 10 minutes before, the airplane had no escape route already. It was stuck. Okay, and this is the kind of algorithm, this is the kind of problems that we want to avoid. And in fact, the reason why I raised this case is because we met the same case in an actual research experiment where the pilots were replaced by a drone. Okay, and we saw the very possibility that you can lock yourself up. And I will talk to you about it later. Other cases of malfunctioning algorithms, maybe because what I would call a lack of conscience, a lack of ability to think forward in time. That was these are not the correct cards, by the way, but this was the the DARPA Urban Challenge around 2007, where the MIT car and the Cornell car ran into an accident. And what had happened is that, if I remember well, the Cornell car was stopped on the side, and the MIT car passed the Cornell car. But then, when you pass a car, at some point you want to come back to your normal lane. And they had not planned that it was possible that the stopped car would restart at the same time as the other car was resuming its normal course. Boom, accident. Again, this is not the right picture, because these are not the MIT and Cornell car, but it sort of shows more or less what happened. Okay, so again, a lack of anticipation. So for these kind of things and the need to anticipate, I sort of wrote something which says, they're called Ariadne, and it says that all robotic operations should be planned, designed, and performed under the constraint that at least one sequence of actions has been explicitly computed that will bring the system back to absolute safety. And this must be the case for any known and significant mishap for the system. Okay, so it is a principle that you should never do anything unless you know that you have an exit strategy in case something goes wrong. And it sounds like completely simple, but it actually is pretty powerful, and I'll show you how. First of all, the idea of always having an exit strategy makes quite a bit of sense on the road. You probably have heard about this thing named defensive driving. Defensive driving is driving in a way that you always have options to exit left, right, forward, or maybe by slowing down. And now, how many people do defensive driving on the road? It's not obvious. I would say that my own little analysis on the road show that most don't. Okay, so they don't maintain their options. The worst nightmare being sort of in the middle lane with a truck behind, a truck in front of you, a truck to the right, and a truck to the left. Then you really feel boxed in. So there is a reason why I call the principle Ariadne is because of the mythology, the Greek mythology. Ariadne was the daughter of a king in Minos and on the island of Crete. And in the island of Crete, there was also this monster named the Minotaur. And this monster, was a calamity for everyone. He was asking for sacrifice, human sacrifice, and all sorts of things. Very bad. So it turns out there's a young fellow named Theseus that came, and it starts with a love story because Ariadne fell in love with Theseus, and Theseus said, I have to go kill the monster. The monster lived in this maze named the Labyrinth, and the story was that if you enter the maze, you never exit it because it's too complicated. And so he said, it doesn't matter, I'm gonna go. So she was in love with him. She thought about a way to get him back after he kills the Minotaur. And the trick was to give a spool of thread to Theseus, attach one end of the thread to the entrance of the labyrinth, and the other end would be in the hand of Theseus as he goes and hunts the Minotaur. So the story worked. He was able to go as deep as he wanted into trouble, yet have a backup solution that would take him out as soon as he is done with his business with the Minotaur. Okay, so that's that's, by the way, the meaning of the Ariadne thread, which has become now part of standard English vocabulary. So There are other examples of that, like how do you take daring actions, but you sort of manage to keep your way out if you want. So there is one which is the story of this little guy who was with his 7 brothers taken to the woods by his parents, but he always had a little doubt as to the parents would ever bring them back because they were pretty poor. So he always left like a few breadcrumbs behind. So in case the parents would by any chance abandon them, he would be following the breadcrumbs to get back home. And that worked pretty well the first time, but then unfortunately, the second time it didn't work very well because the birds ate the breadcrumbs. So there was no way back that could be indicated. So it was a nice attempt. And in French, the little hero is named Le Petit Pousset. And so it's a story, the idea of always maintaining a backup, always maintaining and making sure that you have a way out of trouble. It's been around for quite a while, okay? And the interesting thing is, you see, the parents were very smart, right? They took the kids in like very deep in the forest to abandon them. The Minotaur, the labyrinth was a very complicated thing. And you could go very deep into the labyrinth. Yet, you can manage to keep a link out. And how you got into labyrinth doesn't matter. The algorithm could be very smart, right, to look for the Minotaur. Or maybe the parents could be very smart at trying to lose their kids. I mean, it's a horrible story, I must confess. But, nevertheless, even with these very smart algorithms, you can also have like a rescue mechanism, which is literally tailored to what the algorithm tries and do, which is in both cases to lose you. Okay, so that's important because it is a little bit the spirit of what happens today when we have all these smart learning algorithms that sort of explore incredible, complex areas of where you're going to go, okay, and get you there. Well, you want something which respects the fact that these are very smart algorithms. After all, you should respect your parents, right? And yet, you want a backup solution. And that's possible, okay? So even if the very smart algorithm is actually not so reliable, you want to have you can develop these backup solutions. Let me tell you the Ariadne principle in the air. Who's a pilot here? Any pilots? Any airplane pilots? Okay, so there's one. Ryan? I didn't know that. Okay, so first of all, so the main problem with flying, especially on small aircraft, is the first thing you do immediately after takeoff is figuring out how you're going to land, right? It's the first thing. You take off, and the next worry is, okay, how am I going to land and still be alive? And so depending on the countries, you have different strategies for that. First of all, when you take off, hopefully you have, if you have an engine failure right away, you're going to land right away. Now, when you are far away, when you are flying over the country, where did you learn to fly, Ryan? Where did you learn to fly?
I'm a drone pilot.
Oh, you're a drone pilot. Okay, but let's do it for a drone as well. Okay, because it's also important. You want to know where you're going to land. And but on a small aircraft, the first thing you learn is once you are at altitude. In America, and especially in New England, where it's kind of green, and is look for the nearest golf course. So the idea is you never know when your engine is going to quit. And so what you're going to do is you're not going to fly to your destination. You're going to fly towards the next golf course. So you always keep a golf course in mind, because you never know when this could become useful. And the idea is that golf courses, they're kind of flat, they have like long long areas with like nice and well-cut grass. So they're perfect landing spots in case you run out of your engine. And so I trusted my my instructor that was in the late 1990s. And then sure enough, I find that, yes, indeed, sometimes planes land on golf courses. And the idea is as follows. Suppose that you're on your airplane. If you run out of golf courses, for example, you decide to cross over the sea, or you go over a forest, you are trained to start having a deep feeling of panic inside. Okay? Because you know you're doing something wrong. You know you're doing something wrong. Because if you go deep in the forest, no more golf courses, your engine quits. I mean, you're gonna die, pretty likely, you know, because I mean, you're gonna end up running into a tree if you have a problem. Okay, and this is really like physical. I've done it. I crossed a little bit of water. I've flown over forest, and I really had this feeling like I'm not doing the right thing. I do not have a golf course inside. And if I run in trouble, I will die. That happened, by the way. There was the Source 737 that was supposed to fly from one city in Brazil to another city in Brazil. And the story is that there was a good football match that day, and they spent all their time listening to the football match. And then when the football match was over, they asked each other, so where are we now? And the other guy said, you don't know? I said, no, I don't know. I was listening to the match. And what were you doing? I said, well, I was also listening to the match. And then they figured out they were in the middle of nowhere. And of course, they ran out of fuel and died. So that's the idea. Always plan for an exit strategy. Okay. Now, of course, if you fly in Saudi, maybe the problem is different because there's a lot of flat area. Although I don't know how airplanes behave on sand. There are many areas where the sand is hard. So, yes, so there are areas where it's probably easier to land, so that you have lots of flat land. Okay, but there are also areas where the sand might be too deep, and you probably don't want to land on a dune. So it's of course the strategies differ from one place to another, but there is this sort of necessity to fly. But if you're so smart at flying, why don't you fly and keep a flat area available anywhere you are, so that in case of problem you can land. And so in air transportation, it turns out it is the same. I started talking with air traffic controllers, and you know, by and large, I've been working in air transportation for a while, and people say, on the radio, we hear that the air traffic controllers are super busy and they work very hard. Oh, are we having a problem? Okay. You know, we hear about these people being like super busy, and you look up in the sky and you say, I don't see where the airplanes are, it's empty. Well, so I started thinking a little bit about it last fall. And I started thinking, okay, so what is it that air traffic controllers do that's so intensive in their mind? Even though we see nothing in the sky, or very little. Maybe we're close to Riyadh airport, of course, we see something. Close to Jeddah, we see activity. But otherwise, it's pretty empty. Well, the answer is that all the intellectual work, all the tiring work for the air traffic controllers is not about getting the aircraft to fly from here from origin, say, to destination. But it is to answer a whole lot of what-if questions. Like, for example, what if the weather here closes and I cannot come across the weather line anymore? Okay. What if my airplane has an engine problem? What if one of the 12 or 13 airplanes I have to control gets into trouble? And so much of their work is about planning backup solution. Okay, planning backup solution. And for example, I'm not saying this is the only one they're planning for, but one of the backup solutions they look at is, listen, if I cannot cross this weather pattern anymore, I should have at least the ability to stop my airplane and make it do a racetrack pattern that is just go around. How many of you have been in a racetrack pattern waiting to land? I have. Right? You remember, right? So it's not very comfortable. The airplane is going slow, and it's not a comfortable situation. Well, it is basically as a temporary storage solution while things clear out. Okay, and this is what I believe takes all the minds of the pilot, of the air traffic controllers. It is not the computation of what the airplanes are going to do, but the fact that the airplane is going to be allowed to move, say, further than this point, only if it has a backup solution available as well as wherever it intends to go. In other terms, the airplane will not be able to go past this point unless it has a backup solution shown in light blue here. If it does not, then it will engage into whatever is available now and go into a protective mode, if I may say, a backup mode. Okay? This is quite different from the mentality of, I'm going to do whatever, and then in case there is a problem, I'm going to try and repair. No. Here is like, first I plan for the repair, and then I will make progress towards my destination once I have the repair ready, which is completely different. But it's quite interesting because what? Well, because asking that this airplane move forward here only when the repair is ready is doable with unreliable algorithms. Meaning, all I'm asking for the algorithms to, if now I move to the drone unmanned world, okay, I can take my smart algorithm and say, listen, you already have a backup solution here. You're going to be able to move here only if you have a backup solution there. Okay? All we're asking the unreliable algorithm is to nevertheless give me the backup. Okay? So sometimes it does. Hopefully, sometimes, but not too often, it does not. What happens if it does? If it does, well, I know I can move forward, and then once I reach there, of course, I just, in order to move any further, I make sure I have another backup solution, etc., etc. Okay? But if it fails, well, I already have a backup trajectory, and I will be safe, and I can go and do my turns, at least for a little while, until my algorithm recovers. Okay? Now, the fun part is that we actually did it. So I will show you the example later, but this actually happened to us. So to summarize, the idea of using unreliable components for reliable flight or reliable operation is to ask from these very smart, unreliable or unproven components just to do a little more work than just planning a nominal trajectory. We're going to ask them to plan for the nominal trajectory, of course, but before anything is undertaken, like moving any further, make sure and ask them to also compute the backup trajectory. Okay. Now, the backup trajectories, well, if you think about all the possible configurations that happen in air transportation with weather, with congestion, et cetera, okay, or with maybe geofencing for drones, okay, there are so many of them. You cannot pre-compute all the backup trajectories. There's too many configurations. But do you need to pre-compute? No, you can do it online and sort of compute your backup solution online as needed, okay? And presumably, if your algorithm is so smart, it's gonna find it, okay? Now, if it is not going to find a solution, I mean, at least you're glad that you know that you couldn't find a solution out of trouble ahead of time, okay? Because otherwise it is like, you know, this sort of propaganda where, you know, very American style propaganda, you know, my medication can cure every disease, okay? And then, you know, you say, yeah, but I'd like to have proof, okay, before I use it. That's what we're asking. We're asking for the algorithm to say, if you're so smart, show us not only how to get in wherever you want me to be, but also how to get out of there. If you cannot get me out of there, then I think I will have I would say, our mutual level of trust will be not as high as planned. So, with that in mind, I've been talking to a pilot, and she said, well, we don't like racetrack patterns. When air traffic control tells us that we have to go to a racetrack pattern, therefore a backup solution, we don't like it because immediately we start looking at our fuel gauges and say, if this lasts too long, I'm gonna run out of fuel, and then, you know, I will not be safe at all. So I've been starting to think about how we should, in fact, for a drone or other vehicle. I mean, I'm an airplane guy. So every robot that I draw ends up looking like a flying machine. But I assure you, it also works for ground robots. And I started thinking is that we should plan for the backup solution, maybe a sort of not too taxing backup, but then to be a true backup, there should also be at the end a trajectory that lands you to some airport, named a diversion airport, so that you're sure that once you're on the airport and you're stopped on the ground, you can say, yes, this time I'm really safe, okay? So these are sort of evolutions in my thinking, but especially Dr. Anis and lab members, do you see how all this could carry over to drones? The idea that we do sort of maybe some fancy planning throughout campus, but somehow we always keep in mind, okay, so if I say my battery level goes from like 80 to 10 in 3 seconds because of some malfunction, okay, I always have at least planned for the option of doing like an emergency landing on a nearby building top. Okay, so this is the idea, okay? And it can be implemented in a very simple way or very complicated way, but the idea of planning with a consciousness, meaning planning for not only what you want to do, but also what you could have to do because of unplanned thing, is, I think, very healthy and does not require anything like assured autonomy or whatever. Or to be more precise, it's what I call an actual, very practical mechanism for what people call assured autonomy, meaning autonomy, but with safety. So it has allowed me to start looking at many other of these things where people plan not only for what could happen, but also for contingencies. And I've noticed that in many cases, you see, making the algorithm work not only for nominal operations, but also for abnormal operations, is does not require to understand the algorithm completely. All you want is that most of the time it comes up with a backup solution, because otherwise we're going to end up spending too much time backing up and not enough time doing what we're supposed to do. Okay, and that's very different from what I've seen, for example, in the area of collision avoidance algorithms. There has been a lot of work on collision avoidance algorithms. We're talking about them when we're coming towards this place. So there is a collision avoidance algorithms named ECAS-X, and people have spent a lot of time proving that this collision avoidance algorithm will work regardless of the initial conditions. And what I claim is that it's actually unnecessary, that all these efforts at verifying collision avoidance algorithm, whereby you come up with a statement which says, regardless of the initial conditions for the aircraft, the collision avoidance system is going to work, is unnecessary. All we need to do is check online, okay? And we can guarantee that there will not be a collision. Instead, what we can have is sometimes the unnecessary triggering of what is de facto a backup solution, an avoidance maneuver, even though there was no problem and it shouldn't have been done. So it's a false alarm. Well, if it doesn't happen too often, pilots can live with it. If it happens all the time, pilots don't like it, okay? If the system is always in alarm mode, it's not good. But otherwise, not a problem. No need to do comprehensive verification of collision avoidance algorithms. So you can also see, as I said, the principle as trust but verify. Yes, your algorithm will take me in some direction. I trust it, but why don't you show me evidence that you can take me out of here on a case-to-case basis? Let me add, by the way, that this works not only for planning algorithms, let's say geometric planning, but also activity planning, software management of the software stack. Okay, and I learned that by talking with by talking with one of my students who actually had thought about this concept of trust but verify, go in the direction, but always having a backup solution in mind. And we worked on it back in the late 1990s, as well as early 2000s. First, at the level of dynamical systems, okay? It was a problem of how do you go from some origin to some destination if we don't have a proof that we can go directly from there, but we have intermediate objectives. So the idea is to say, what I'm going to do is I'm not going to plan directly for that objective. Instead, I'm going to plan for going to this first intermediate objective. But as soon as I am within what I would say a guaranteed region of attraction of the second objective, I'm going to stop going to my first objective, and I'm going to hop to the next objective. And as soon as I am within the region of attraction, the region where I know I can get there, okay, I'm going to stop going to that second objective and finally go to my final objective. So all this, at the time, we published in the IEEE Transactions on Automatic Control. By the early 2000s, we started publishing in robotics journals. And the student who was working on this implemented all this in a automotive self-driving car company named Autonomy that he sold back in 2017 for a few $100 million. And he finally paid his dues to the companies that bought his startup. When a startup is bought, they buy everybody, right? And they ask the founders to stay at least 3 or 4 years so that they do effective transfer of everything before they're allowed to run free with the stock and they can cache the stock. So he actually did that pretty much the day you spoke at the robotics conference, Dr. Anis, and he was one of the speakers at the robotics conference. And finally, he was able to speak his mind about his view of the future of self-driving cars, okay, which he was not able to do for a number of years. So just to say that these ideas, as I said, are very old, and they have been progressively and constantly updated, and they are present in today's self-driving technology, okay? At least the one that seems to have been meeting practical success. All right, so I'm gonna skip some of this. I want to talk a little bit about this implementation. That was an experiment we did years ago, where we used exactly the same philosophy in order to fly an unmanned aerial vehicle safely. We wanted the unmanned aerial vehicle to do a complicated mission that we could, whose trajectory we could obtain only by solving what's called a mixed integer linear program. Yes. And you want to do something, Rod?
Yeah.
Okay. It comes straight out of operations research. And the good thing about mixed integer programs is most of the time they run well, but sometimes they don't. And we don't know when. So it was a perfect example of what I've been talking about here. What we did is we said to that aircraft, okay, you can go ahead with your mission as long as over the near future you have a backup trajectory that's computed. And it was a racetrack. And guess what happened? During the first test, because our implementations were bad, the vehicle was just doing racetracks. So he was going from racetrack to racetrack. He was making hardly any progress. Okay, he just stayed in a racetrack. At least the pilots told us that at least our software did not take them like others over Los Angeles, because we were flying north of Los Angeles. At least our software, because he was cautious, because he always had this backup solution available ahead of time, did not take the airplane over Los Angeles. Let me add that, I wish we flew this aircraft. It was an unmanned vehicle designed by Boeing. It was named the JUCAS at the time. Instead, they gave us the T-33, which is an airplane that dates back to 1948. But they promised they had retrofitted it with the same electronics as this $1 billion aircraft. So that was sort of an interesting experiment, but I didn't know the value of the experiment until I realized that it was not only like just an idea that we've thought of in the lab, but in fact it was the mentality, for example, used by pretty much all pilots and all air traffic controllers in today's flight operations. So let me finish. I'm sorry, I'm running a little bit over time. I apologize. Let me show you, of course, where there are some problems. Well, each time you have to go to a backup solution, you waste time. And let's face it, there are some cases where you cannot do that. You're forced by the tempo. And so you probably remember this. It's the Starship of Elon Musk and SpaceX. And as you know, it has always gotten into trouble so far. Okay, so here you have an operation, and the tempo is so tight, and the fuel reserves are so low that contingency planning is impossible. It either works or it does not. Okay, did not. And so in those cases, if we were to enable any kind of proactive backup, of course, we would need to have fuel reserves. We would need to have all sorts of things that would probably adversely impact the economic value of the proposition of recovering the spacecraft after, or the rocket after takeoff. Okay, so I just thought that it was it's an important remark to say. I am not here to give a launch about give a talk about free launches. Okay, there is a famous theorem in math that says the no free lunch theorem. Okay, you do not get anything free for free. Okay, or anything good for free. So, of course, I'm thinking about this in the context of urban air mobility in the future, and there are applications in human-robot interaction as well. There are applications in air traffic control that I've already talked to you about amply. And at this point, I would like to thank you for listening to me.
Thank you very much. Okay, thank you very much, Eric. It was a very nice presentation. I really like it. Everything also. As the public have any question to Professor Eric? Yes.
So thank you very much for the very insightful talk. I have a question. Is it always possible to have an exit plan?
To have what?
An exit plan.
So I talked with one of my students who just became a pilot, and he takes off from an airport in Atlanta, and after takeoff, wherever he sees, there are only houses. So he has no backup, and he feels very uncomfortable with that. So you can nevertheless quantify the amount of risk you're taking when you don't have a backup. Instead of taking a 0-1 approach, what you can say is, well, maybe I can fly without a backup as long as it's only 15 seconds. Okay, in which case, of course, the risk is whatever it is, but it will remain low. So it will be sort of transforming all that I said from what I would call a worst case deterministic viewpoint to a more stochastic viewpoint, which is possible. But definitely, we know that we do lots of things without a backup, even though in many cases we should not really.
I guess sometimes it's costly as well to have a backup plan for every situation.
So in air transportation, and that's one of the keys to understand why it is moving so slow, meaning it's evolving so slowly, they have to have it. Have to have it. The system is amazingly reliable. You fly 1 billion miles, the probability of, or the number of deaths you're going to experience over 1 billion miles of air travel is 0.02 death. Okay? Your risk of dying of a heart attack is a lot higher than that. Okay? As a comparison, the helicopter is a case where you don't work with a backup plan a lot. And you know how many times you die when you travel 1 billion miles in a helicopter? 280 times. Okay, it is by far one of the most unsafe transportation mechanisms you can think of. And by the way, I don't know if you follow the news, but there is at least, I mean, we hear at least 1 or 2 billionaires dying every year. Kobe Bryant, the heir of the Dassault family, the airplane maker in France, and then most recent, that was about a month and a half ago, and then 2 weeks ago, it was the richest man in the Czech Republic. Okay, don't fly helicopters. Okay, if you don't have to, don't do it. And so there are like many machinery, many pieces of machinery that do not have a backup, and that really hurts their ability to fly or to operate reliably. On the other hand, you don't want the helicopter to fly only like 3 centimeters above the ground so that it lands, that it can land without killing anybody. So you see, there are some cases where you are in impossible situations, and my recommendation is just walk away from them. Okay, in a car, you can. The number of times you die when you travel 1 billion miles is 7. So dying 7 times over 1 billion miles is something to think about, but it's much better than dying 280 times.
Okay, thank you.
Professor, thank you for the beautiful presentation. I have a question speaking of air transportation. Do you think anytime soon we could switch from manned aircraft to unmanned aircraft totally? And would you trust it?
So this is exactly one of the points that I wanted to make. You see a lot of promise about unmanned transportation, air taxis, and things along these lines. You hear about some air taxi operation taking place in Dubai, if I remember well, in the UAE. Well, it doesn't seem to be going as fast as what Uber anticipated and as fast as even UPS anticipated, and so on and so forth. Amazon, of course. And one of the reasons is because precisely what I talked about, which is that, and this is normal in a very entrepreneurial world, you don't want to think about the bad problems. You don't want to plan for the bad. You just go, right? But what goes well, or what works well for developing an app, doesn't work this well when you involve physical artifacts. And as a result, now what you are seeing is that many of these companies who thought that the hard part was to design a vehicle that would look fancy. You've seen those interesting vehicles, very nice, very fancy, new components, fiberglass everywhere, carbon, multiple propellers, etc., etc. Now they realize that is not the problem. The problem is to get the people from air traffic control to agree. And for them to agree, everything must be built in such a way that they know this machine will be operable not only during good conditions, but also if something goes wrong. Okay, and this is how they're used to doing it, and that's why they are like pulling the brakes and say, wait, not so fast. I was talking, in fact, about this idea to the executive director of the European Air Safety Agency, Patrick Key, the guy who said no to the MAX. He said, we will certify the MAX separately from FAA because we're not happy with the way the 737 MAX was certified in the first place. And he told me, this is exactly our approach, and this is exactly our main problem. He said, each time there's a new possibility of failure, we have to anticipate for how we're going to handle that failure. And each time we anticipate how we're going to handle that failure, it does like the defensive driving thing. It kills capacity. We cannot operate as many systems as we would like to. And so one of the reasons they are worried about self-flying vehicles is that they're not really self-flying. They are following the same scheme as the one that has been in operation by General Atomics since 1990. There is a remote pilot. And the big problem is that the remote pilot is considered just like if the pilot were sitting in the aircraft, with one big difference. There's one more data link. There's one more radio connection. And they say, if that radio connection fails, We have to be able and plan for that. And as long as we do not have the ability to plan for that, or as long as we cannot guarantee that the data link, the radio communication, will be working with probability 0.9999999 with a certain number of nines after per hour, we will not accept it. We have to find a backup solution. So they thought about a backup solution. I talked with air traffic controllers, and they say, you know, the backup to remote flight is autonomous flight. So the backup to having a remote pilot is to go fully autonomous. But probably with precautions, like for example, okay, so the airplane will go fully autonomous, but we will clean the airport of any other aircraft so that this one can land nicely without any problem, without any kind of fantasy, local fantasies. And then this is where they say, the decision makers at the high level say, okay, guys, maybe, but you know, we're going to lose a lot of capacity at this airport. And what you're telling us is that we're going to have to use the airport at half capacity just because of that, and they don't like that for obvious economic reasons.
I think human lives and growth are the main two categories.
Absolutely.
For the sake. Is there any other? Are there any other categories you consider when you think about safety in robotics or anything?
No, I think it's. I would say these are the most important, really, and then of course, you know, the impact, and sometimes it's both, right? Look at the 737 MAX. So are you ready to fly in one? Okay, I actually am. I think they did their job now, but the image has been forever destroyed. Yes, and by the way, I don't know if you noticed, but that's what they did for Ryanair. The 737 MAX is not named MAX anymore. It's named 8100 or something like that. So we changed name. You're rebranded, and it's a really poisonous problem. We just met at our level, you know, humble economic level in the education work. I made a little company because I think that hardware is really important for students to really learn the techniques that we teach them. And it's been working well until now. And this semester, 10% of the Arduinos that we're using in the hardware are faulty. And I'm having nightmares. I think I don't know how I will repair that. Of course, it's not as embarrassing as Boeing. I'm not going to lose $18 billion, but still, I'm planning. I don't know how to do that. I don't know how to handle this. I know the students are mad, and I know that there has been some damage because what? Lack of foresight, lack of planning for the future. But on the other hand, if I put a triple redundant Arduino in my machine, then it becomes unaffordable. Okay, I would rather have a triple redundant chip system on my laptop. That would save me a lot of anxiety.
And should time frame of projects, like project time frame, should allow us sometimes to take off these images for backup plans?
Say it again.
Project time frame. Like sometimes you have to finish a project on robotics that you should start in a specific date. Should that let us think about taking off the safety plans?
Well, yeah, exactly. Well, that's the case of that rocket. Okay, it doesn't have much time or it doesn't have much fuel, so it cannot. It has to evacuate. And well, I guess at least as long as you know that there was an issue and you know that you are evacuating the backup plan because of constraints in time, I guess it's okay. At least you can write it somewhere, say, I knew this would be the case, and you have but you have Professor Annie's sign on this before you move forward. And then you're fine.
Thank you very much, Eric. It was a great pleasure. I have so many questions, but I'm going to talk with you later.
With pleasure.
Yeah. Okay. Thank you very much, everyone. I appreciate it. Okay.
So you Ariadne algorithm. So have you implemented any AI combination with Ariadne?
So the answer is yes. So it all depends on what you call AI, of course. So the most fancy algorithms that we've implemented with this kind of philosophy in mind was path planning algorithms that would use randomization. So their name like RRTs, randomized, rapidly growing random trees, RTs, yes, and things along these lines. So really, there is a flip of a coin at any instant, you know, to build a path. So it's typically the one where you have no guarantee. But nevertheless, with this kind of thing, you can implement this and nevertheless remain safe. And in fact, this is one of the pictures that I showed. And this is how we said, yeah, we can work with RTs and be safe, because what we do is we're going to engage into a branch of the RT only if we know that at the end of the branch, there is a safe condition. Now, safety may differ for different systems. Safety may be for a vehicle, like the vehicle is going to be able to stop, or it's going to be able to enter a racetrack. Maybe if the device instead is a health device, like a radiotherapy machine, it will be that the endpoint is the beam of particles has stopped and all mechanical parts are stopped. Okay, it all differs depending on the specific application in mind. But I've read a lot about stories about radiotherapy machines that stopped in an unplanned manner. There was no backup, there was no nothing. The computer froze, and there was a patient in the machine, and the operator did Control-Alt-Delete to restart the machine while there was a patient in the machine being beamed, and unfortunately, it was at full power. So we're really, I think, talking about trying to make AI and all these sort of advanced algorithms work, have us reap the benefits of these algorithms, but without giving up on safety.
Okay. Thank you very much. Just to finalize this, I think flying this drone is very important. And I remember in my early days when I wanted to fly a drone, and I was very much worried about the flyway. So the best solution I found is that I have to attach it with a thread. So when it flies away, just put it back.
Like come back down. Yes, well, yes. And this is why, by the way, usually CAPA and FAA and other administrations don't have too much of a problem if your drone is attached. Yeah. As soon as there is no attachment point, if there is no string attached, it becomes a problem. Yes. So before you look at the contract and says, oh, there are strings attached, watch out before you cut the string. Okay, you may get yourself in trouble. You may gain freedom, but you may get yourself into trouble. Hey, I think this is great for administrators. Yeah. I should say that. If you think there are strings attached to your contract, just cut the string and become free and see how you feel about it.
Okay, thank you very much, everyone. Okay, thank you.
Thank you.